So I'm going to start recording here for those people who are unable to attend the session live. We're going to be doing a mole lab, and I just shared the document with you in the chat so you can open it. If you do open it, go ahead and make a copy of it for yourself. Right? If you're not sure how to do that, you go to File, Make a Copy, and then you can actually title it your name, mole lab, right? Something like that so that you're able to locate it again in your Google Docs. So we're going to read through some of this background. We kind of talked about moles a little bit already, but we're going to talk about them in more depth. Sorry, Oliver, I probably did the link before you logged in. There it is. We're going to talk about molar mass again, which again is something that we discussed in the last virtual session. We did not go over it more than once though, so we're going to talk about it again. We're going to talk about how to find molar mass, and then I actually have some fancy chemicals. They're really not that fancy. I have calcium chloride, which is essentially like road salt to help melt snow, and glucose, which here it's in its dextrose form, but it's the same chemical formula. So we're going to be looking at these two solids and also water, which is the easiest thing to use. And we're actually going to calculate some molar masses, atoms, and mole amounts based on an arbitrary amount that I record here. So make sure that you've made a copy of your document so that as we're going through this, you can be writing in it, right? We'll do, we're going to do one of them together, and then the other ones you will do the math on your own. So that way it's kind of all set up here with an example, right? So if you get stuck, there will be examples to look back on. So, do we have a volunteer who would like to read to us about the mole? And if not, would you guys like me to read to you? Because I can certainly read to you. But I thought I would ask. Well, thank you, Bella. So go ahead and unmute yourself if you are in fact muted, and please read for us the background, the first two paragraphs here about what a mole is.
Okay. Because samples of matter contain so many atoms, scientists use a counting unit called the mole. The word mole represents a number, just like the word dozen represents the number 12. The only difference is that a mole represents a much larger number than a dozen. The number of particles in a mole has been experimentally determined in a variety of ways. A device called a mass spectrometer, which can count atoms precisely, was used to determine the number as 6.02214 times 10 to the power of 23. We will round this number to 6.022 times 10 to the power of 23. This number was named Avogadro's number to honor the Italian scientist Amedeo Avogadro, whose ideas were crucial in the early understanding of chemistry.
Awesome, thank you. Right, so a little context of where the name comes from for this number, right, and what the number is. We round, right, if you'd like to use the official number, 6.02214, no one is stopping you, right? I will totally accept the rounded version of this number. But really, when we talk about moles, we're talking about a big number of atoms, right? Because if we really wrote this number out as a number, it would be huge. 23 decimal places after that 6 would be there. I don't even know what number that would be. It's bigger than, is it a good, I don't even know. Once numbers get that big, I forget exactly what those prefixes are supposed to be. But if you do know, please let me know. Molar mass, I'm just going to quickly touch on because we did talk about that in the last virtual session. But remember, this is something that we get from the periodic table. And I emphasized last week, make sure that you have access to a periodic table. You can print one, you can have one open in a tab, right? A lot of this stuff you're not going to be able to do if you're not looking at a periodic table. And don't just try to remember what you think it says on there, right? Always check, even if you think you know the mass of something, just double check. So molar mass is actually going to be telling us the mass of 1 mole of a substance in grams. So we talked about this a little bit last time. But I will quickly review periodic table as I like tell you guys to have your periodic table open. I don't have mine open, right? Not a very good model there, but that's okay. So if we look at the periodic table, all of these masses that we see listed on here, for example, boron 10.81, that is telling us how many grams of boron are in 1 mole of boron. Whereas if we look at something like 10, we see that in 1 mole of 10, we have 118.71 grams, right? So there are more atoms of 10. Wait, no, that's not true. There are less atoms of 10 for the same amount of boron, essentially, because of the way that these masses are listed here. Unless I might have said that backwards. My brain is not 100% working. These afternoon sessions are hard for me. We already had like hours of meetings today, so I'm just like, okay. So regardless, we will digest how we're going to use this in this lab. So molar mass is on the periodic table, right? This is an example. We did this a little bit last time, but just in case you want to try this one, in fact, I probably should have erased this, so we could have tried this as a group, but we'll try another one as a group. So if we are told that we have 3.25 moles of fluorine, and we want to know, well, how many grams is that? Okay, Chris. Then we would set up dimensional analysis to figure this out, right? I told you here the molar mass of fluorine. However, if I didn't, you could always go back to your periodic table, find fluorine, and you would see that the mass of fluorine is 18.998, right? So that's taken directly from the periodic table. So in this case, we start with what we know. We know that we have 3.25 moles. We know that we have 18.998 grams of fluorine in 1 mole. So then we just set up a nice, simple, one-step dimensional analysis question here, where our moles will cancel. We're going to be left in grams, right? We are asking what is the mass. So that's a good thing to check too. Are you actually answering the question that's asked? I know sometimes with dimensional analysis, I get a little excited and go beyond what we're supposed to do. Would anyone like to multiply that out and suggest what we should get here for our answer? And I'm going to challenge you to also put the correct number of sig figs. So still waiting on people to suggest the correct answer here with the right number of sig figs. Thank you, Oliver, for giving us the number here, 61.7435, right? All that you had to do to get this number was multiply 3.25 times 18.998. Now, how many sig figs, though, would we have? How many sig figs are in the number of moles that we were given here? 3. How many sig figs are in our molar mass? 5. So do we do 5 for our answer? Do we do 3? Do we do something in the middle? What is the rule here for sig figs? And you might not remember, right? I like how Oliver's guessing. Do we do 3? Yes, right? So you always want to go with whichever number is the least precise. 3.25 moles can never become more precise because that's as precise as you were given, right? This number could go on probably even more. It doesn't matter, right? We have to go with what the least amount is. So in this case, we're going to have to round this number to 61.7 grams. Now, I personally, I like to write out the whole number each time and then figure out my sig figs. You could always just do it straight from your calculator. But I know one of the students that I tutor in chemistry, she always erases the number and then rounds wrong, and then we have to do all the math again. So make sure that you have it written down somewhere if you think you're going to be needing to figure this out. But it's going to be the least amount of sig figs. So this would be our answer here to this question. What is the mass of 3.25 moles of fluorine, which has a molar mass of 18.998 grams? So now, why don't you guys try to set one up on your own? It's going to be very similar. Let's say that we have 0.037 moles of 10. And I want to know how many grams is that. So 10 on the periodic table, which the reason I'm giving you this one is one of those weird ones that does not have a T in it anywhere. If it takes you a while to find it, that's totally normal, right? But 10 is right here, it's number 50. Give you a little hint on that one. Otherwise, see if you can set up a dimensional analysis to figure out how many grams of 10 there would be in 0.037 moles, and challenge yourself to pick the correct amount of sig figs. Oops. Okay, so just in terms of time here, I'm going to kind of push us through this a little faster. Hopefully you set something up like this. Your number of moles, 0.037 moles, times the molar mass that you got from the periodic table, which for 10 should be 118.71 grams per mole. Did anyone get an answer from this with the correct amount of sig figs for how many grams that would be? Okay, Bella says 4.392 grams, I think. Okay, that is the correct answer. Now let's talk about sig figs. How many sig figs are in the moles that I gave of 10 here? I know everyone's looking at that first zero and the second zero and thinking, are they significant? So the correct answer is 2. That is a terrible 2 that I just drew. This 0 is not significant. And any zeros in a decimal that are not surrounded by whole numbers are not significant. So neither of those zeros is significant. And I know especially this second one might be mind-blowing too, because you think that is a placeholder. Of course it's significant, right? It's technically not. So there are only 2 significant figures here. So then based on that, Bella, how would you round your answer? Notice I didn't even look at the other one because I know it has more than 2. 4.4, right? So the answer to this question would be 4.4 grams of 10 are in 0.032 moles. Okay, that part shouldn't be too bad. Now we want to think, okay, well, how does this apply to chemistry? So practicing measuring techniques, hopefully most of you know how to record the mass of solids, liquids, right? We don't really record the mass of gases, at least not in our laboratory situation. I'm going to be modeling how to do that for you today. But if you do take an upper level science course, you will get to do that on your own. So it's going to be completely arbitrary here. I'm going to tilt my camera down so you guys can see my scale. So here's my digital scale. I personally like to use digital scales because I'm lazy and triple beam balances are really hard. You might be able to see, unless it's upside down for you, that the scale is zeroed. It says 0.0. Well, I'm going to be using a piece of paper here to measure first some mass of my calcium chloride, which actually kind of looks really cool. That's why I picked this. So it looks like little Dippin' Dots, right? That's what calcium chloride looks like. It is a salt, right? It is used typically in, not Dippin' Dots, but in breaking down snow and ice on roads. So in order to be able to weigh the mass of this without putting it directly on the scale, right, because I don't know if it's harmful. I mean, I do know it's not harmful, but just in case, I'm going to use this piece of paper. So I'm actually going to zero my scale with my piece of paper on it, which in fact, the paper weighs so little that the scale does not pick it up, which is great. I checked that my scale is in grams, which you guys might not be able to see, but it is. And I'm going to put my sample of calcium chloride, and of course it's little tiny balls of salt here, so being very gentle here so it doesn't roll off. I could have also used a solid container, done the same concept, just zeroing out the paper, or excuse me, the container instead of the paper. Okay, so there's my beautiful mountain of calcium chloride, and I am recording a mass of 4.1 grams. So in your data table, under mass in grams of calcium chloride, you're going to put 4.1. Now notice that the scale doesn't go further than that. It only has 2 sig figs. We are going to be staying with 2 sig figs for every single one of these, which is going to feel limiting, right? You're going to want to put all the decimals, but you don't have to. Okay, so that was the mass of calcium chloride. Now I'm going to do the same thing for glucose. So I'm going to say goodbye to my calcium chloride. I'm just going to put it back in the container, which is not a necessarily good chemistry practice, but in this case, it did not really touch anything, and I cleaned the scale before. We're going to do the same thing with a different piece of paper, just in case there's contamination, for glucose, which a lot of us are probably familiar with glucose. It looks like sugar because it is, I'm not in the camera, there we go, because it is sugar, right? It's regular table sugar. So glucose, much more powdery than the calcium chloride. I'm putting the same volume of glucose, right? I used a 1 teaspoon measuring spoon here to get the same volume of both of these. However, I have a different mass. My glucose mass is going to be 3.1. So mass of glucose, 3.1. And then finally, water, which is going to be the hardest one because I hope this scale will pick it up. I'm going to use a beaker. I'm going to set it on the scale, and the beaker does weigh quite a bit. It weighs 456 grams. So I'm actually going to zero the scale with the beaker on. So now it says 0, even though there's nothing in it. I'm going to pour my sample of water in to see how much the water weighs. And, ooh, what a nice even number. Our water is going to weigh 65.0 grams. Okay, so, for example, in a real chemistry lab, this is something that chemists would do, right? You'll see later on in the course, sometimes you have to create a solution where you have to put a certain amount of something in water. Sometimes you will need a certain amount of moles for a reaction. So these are real skills. Like, it seems easy. Oh, you just measure it. Well, yeah, but now we're actually going to calculate the moles and the atoms that are in each of these samples. So I did an arbitrary example here of sodium chloride, which is regular table salt, to show you a full example of how to do this. Then we're going to do a little check-in. If you feel like you can do the math on your own, you're going to be able to leave the session. And if you'd like to do one example together of the three that we have recorded masses for, then we'll do that one together. So here is an example not related to the math we're going to be doing for our samples, but let's say that we recorded a mass of 20.2 grams of sodium chloride. We're going to look at the periodic table to find our molar masses, just like we did before for fluorine and 10, right? We read straight off the periodic table that sodium has a molar mass of 22.99 grams per mole. Chlorine has a molar mass of 35.5 grams per mole. There's only one of each. So we talked about this last time, where complicated equations, which all of the ones I gave you, have something that there's two of. Right? If there were two sodiums, for example, we would just add two 22.99s into our final molar mass. If there were 30 sodiums, we would add that 30 times. So really, it's just about looking at the formula and figuring out how many times you need to include each element. So we add those two numbers together, which I guess I rounded, not sure why I did that. And we got 58.5 grams per mole is our molar mass of sodium chloride, right? So we found the molar mass of a compound here instead of just one element. Then we do the same dimensional analysis that we did in the beginning, where, except it's flipped. This time we're starting with grams and we're going to moles, right? In the first example, we started with moles and went to grams. But what you should be noticing is that this conversion factor can be either way. Grams can be on top, grams can be on bottom. You can flip it as you need to. Why can you flip that conversion factor? Does anyone have an idea of why you're able to do that? Thank you, Oliver, because it equals 1, right? We're saying that 1 mole and 58.5 grams are equal. That means we can flip it either way because it's still equaling 1 in the end. So be mindful of that. Sometimes people get stuck on that. They don't want to flip it. They think, oh, I don't know. You can do that, right? And that's actually, you're going to have to do that a lot of times. Okay, so if we do this math out, we get 20.2. We divide by 58.5, and we get 0.345 moles in our sample. I guess I must have rounded so that we could stay within 3 sig figs is what I'm guessing is what I did. So in the end, we have 3 sig figs, right? Remember that first 0 is not significant. And then we have 0.345, all of which are significant digits. Okay, that part probably doesn't seem that complicated, right? Now we're going to go to atoms. This is where we're going to use Avogadro's number. To convert to atoms, we have to know how many moles. So in some harder questions, you might see questions going from gram to atom. You can do that, but you're going to have 2 steps, right? In this case, I broke the steps down so that you can just do a simple 1-step equation twice, really, or not equation, but dimensional analysis. But regardless, you can incorporate this into a longer dimensional analysis, which we'll see later in the class. So we just take our moles number, which we got from our previous setup here using grams, and we multiply by Avogadro's number so that we can get rid of moles and be left with atoms. Now, these are all going to be huge numbers because you're multiplying by 6.022 times 10 to the 23rd power, right? That's a huge number. So unless you have like a really tiny amount of moles, you're going to have a lot of atoms. So in this case, I did not round to the correct number of sig figs. Does anyone want to help me correct my answer here and tell me how many sig figs I should have and what my answer should be rounded to? I should have 3 sig figs. Good, Bella. So I see 1, 2. This 7 I need to round, right? It looks like I'm going to be rounding it up because it's next to another 7. So my final answer should have been 2.08 times 10 to the 23 atoms in our sample. Now again, that's a ton of atoms, right? But remember, atoms are tiny. Of course there's going to be a ton. Okay, so now you're going to do that. It's just a great way to practice the math and molar mass for all 3 of these samples. You have the grams, you have the periodic table so that you can figure out molar mass. You're going to calculate the moles in the sample and the atoms in the sample. And that's where we're going to do a little check-in. So type a 1 in the chat if you feel like, okay, this is not so bad. I can do this by myself. I'm ready to go. You're going to tell me that you're ready to go, and then I'm going to actually tell you that you can leave if you'd like. Okay, Bella, you are free to go, right? You're welcome to stay if you want to see the example. But if you feel confident that you can do this by yourself, go do it by yourself, right? You'll probably finish before I even finish the example. Everybody else, I will take your silence of not typing a 1 to mean that you want to do an example. Okay, bye, Bella. Oh, Vitali, okay. Vitali, you're free to go, right? If you feel like you're ready to do this on your own, go ahead. Everyone who's left, who's telling me that they're not quite confident in doing this by themselves, which compound would you like for us to do together? Should we do calcium chloride? Should we do glucose? Or should we do water as our example? Okay, water. I like it. So our mass for water was 65. Keep that in mind. I'm going to come down here to a nice blank space. Get my dimensional analysis table in. Okay, so first step is we want to figure out how many moles are in our sample. Well, we know our mass is 65 grams, 65.0 grams. Now that 0.0 becomes important because I am saying that that is a significant figure, right? That's going to help me in my answer, knowing that I have 3 to start with for water. Now, what do I need to know in order to convert this into moles? And if you don't remember what the thing is called, right, you could say like periodic table or something. I don't know. Give me a hint about what we would do next. What do we need? Yes, we need the molar mass is the technical terminology, but it is also equivalent to the atomic weight, Logan, so that is excellent. So we're doing this for water, right? So water is H2O. We have 2 hydrogens and 1 oxygen. Guess I'll write out full word of hydrogen here. So we need to look up the molar mass of each one of these. Hydrogen, you'll probably have memorized eventually because it's a pretty easy one and you use it frequently, right, is 1.008. And oxygen is 15.999. So 1.008 is hydrogen and oxygen is 15.999. Okay, so then to find out the total molar mass of water, what are we going to do? I'm writing out what we're going to do. If you're not sure, maybe you can try to put that into words. Thank you, Logan, for putting it into words. Well, we have 2 hydrogens and 1 oxygen. So all we're going to do is take these numbers and apply that concept here. We have 2 hydrogens, so 2 times 1.008. And then we only have 1 oxygen, so we need to add our oxygen, which gives us, I would say, try to do the math with me so you can make sure that you don't need that explained, right? Because I can definitely explain the math, like what you actually type into the calculator, if that is confusing to you. 18.015, also what I got. And I'm not rounding anything yet for sig figs because I'm in the middle of solving this question. So I'm going to keep as many sig figs as I can until I get to the end. I always go off of what was given to me in the question or what I recorded in the lab. So in this case, 65.0 grams is the only thing I was given, right? The rest of this stuff is other information that I wasn't necessarily given. Okay, so then now I'm actually going to plug in this information, and I'm going to need grams on the bottom and moles, no, not big G's, grams, there we go, and moles on the top. Why? Because I want to cancel grams out, and I want to find the moles. So now I just plug in what I know. We didn't write the units here, right, which is probably bad news generally in chemistry, but this was grams per mole that we found here, 18.015 grams per mole. So that means I'm going to put 18.015 on the bottom and 1 mole on the top, because I'm saying this is how many grams of water there are in 1 mole. Then I'm just going to go through my math. Grams cancel. We're left with moles. I'm going to be dividing 65 by 18.015. And what do you guys get when you do that? Oops, if I could type into the calculator correctly, that would help me. There we go. 3.608. Good. And now we have to think about sig figs. So I only have 3 sig figs in my original number that I found. My molar mass has 1, 2, 3, 4, 5, right? So I'm not going to use 5. I'm only going to be able to have 3. So I'm going to have to round my answer to 3.61. Because that will give me 3 sig figs. And again, I want to include my unit, which is moles. Excellent job, Oliver, saying that in the chat while I was busy thinking in my mind. Okay, so then where does that number go? Well, erase a bunch of stuff. That's going to come into your data table for your moles in the sample. For water is 3.61 moles. So finally, we have a mole amount that's more than 1, right? Although the first question I think had a 3, but still. So that 65 grams of water is actually 3.61 moles. Okay, now we have to figure out the atoms in our sample. So I'm going to give you guys a second to see if you can set up what we need to do to find the atoms. Feel free to scroll through the document, right? Remember the example that you saw. You will need Avogadro's number here. So try to set up what you would need to do to find the number of atoms in our water sample. I'm hearing somebody. Okay. I'll give you a hint. You're starting with your moles. You are indeed correct, Logan. We're going to multiply by Avogadro's number. 6.022 times 10 to the 23rd power atoms in 1 mole. So in this case, moles will cancel. We're left with atoms, and all we have to do is multiply. In this case, we'll still have 3 sig figs because we rounded previously, right? That's fine. So what do you guys get when you do that math? Thank you, Logan. You were ready. It's like you were reading my mind there. 2.17 times 10 to the 24th atoms are in our sample of water. And again, that's a huge number. Makes sense. Also, 65 grams of water really wasn't that much, right? It was a pretty tiny amount. I'd say it was like 1/8 a cup or something like that. So that gives you a vision for how many atoms would be in, for example, like a large cup of water. It would be a ton. So many atoms. Okay, so about 2 septillion. Oh yeah, Logan, where were you earlier when I was asking how many 10 to the 23rd, what prefix that would be? I didn't even know what it would be. But yeah, septillion, that sounds about right. Very, very huge number. So then in your data table, you would just write in 2.17 times 10 to the 24th atoms, right? You don't have to include the unit necessarily because I told you the unit up here. You're welcome to, though. It's good practice for this class. Okay, so now you guys are going to do the other 2 by yourself. So using the mass that we collected, well, that I collected for you, of calcium chloride and glucose, you're going to figure out the moles and the atoms. Keep in mind, glucose is going to be the biggest molar mass here, right? C6H12O6. That means there are 6 carbons, 12 hydrogens, and 6 oxygens. Calcium chloride will be much more similar to water in terms of how you figure out that molar mass. But otherwise, that is the end of this virtual session. You are now going to go on your own. Oh, I will tell you the code word, although Bella and Vitali might have already left. I will remember that they were here for that. Why don't we have our code word for today be this that I just typed in the chat. That code word will actually give you 100% full credit on this lab, right? If you don't know the code word because you're watching the recording, you will lose 10% for not being here. So you won't be able to get 100% even if you get every answer correct. All right, does anybody have any questions about what you should be doing? I need to make sure that I published this so that you can turn it in somewhere, which is what I'm going to do when the session ends. But otherwise, does anyone have any questions about maybe something that you don't understand that you'd like me to repeat, or a question about the class generally? Yep, you can just write salt in the text entry. You could even include it in your lab. You could write it at the top. Oh wait, I just said the code word. Oh, we have to change the code word. Sorry, Vitali. We're gonna change it to this now. Which I won't say out loud. So you write the code word, yes, you can write it on the lab, or you can write it in the comments when you turn it in. You can write it anywhere. You know, make it so it's easy for me to see. If I have to like read through your lines and it's like hidden, that makes it a little harder. Of course, if I ever take points off and you think I shouldn't have, you just email me. But there's our new code word now. Okay, so new code word, make sure you got it written down. Otherwise, that's it. So if you do think of a question or you get stuck on one thing or you want me to check something, please let me know. And I look forward to seeing you show your work, right? Please show your work so that if you do something wrong, I can figure out how to help you. All right, otherwise I will see you guys next week.